Thanks everyone for having me here to present my work. So this work is funded by the GeoX network. So this is a regional research network that aims at combining geoscience with new data science approaches. And here I use data assimilation to estimate material parameters rather than the state of the system. To understand better the materials that we find on an asteroid, which is called 162173 Ryugu. So this work is part of the Hayabusa2 mission. This is a sample return mission, which was launched to this near-Earth asteroid in 2014. The main orbiter carries 4 instruments and impact experiments and 3 landing devices. 2 samples have been successfully taken 2019, and last year these samples were returned to Earth safely. Why do we study these asteroids? In particular, this asteroid Ryugu is one of the most primitive objects in the solar system, and thus understanding the material of this asteroid gives you insights into the very early stage of the solar system. Part of this Hayabusa2 mission was a box-shaped lander called Mascot, and you can see here in a photograph of this Mascot lander attached to the side of the main spacecraft. And this photo, you see you can see the lander descending to the surface of Ryugu, 2018. So this image was taken from the main spacecraft. It also carries 4 instruments, a camera, a spectrometer, a magnetometer, and the instrument that I work with is a infrared radiometer called MARA. Now, with this instrument, we measure the temperature on the surface, and we measured the temperature of a single individual boulder on Ryugu. And we are interested in the temperatures because when you look at how the temperature changes with changing illumination, you can learn about the structure of the material. And the structure of the material and the temperatures are linked via a material property called thermal inertia, which is the central property which we're interested in here in this work. Also, this instrument features 6 channels, each of which covers a different part of the infrared spectrum. And this can be used for identifying the materials that constitute this boulder. You can see the boulder that we observed in these lower images. This is during day, and this is during night. Here it is illuminated by an LED array which is integrated in the camera of the lander. The red spot shows you the part that we're observing. The temperatures that we observe are on this right side plot, and you can see, which is typical for airless bodies like this asteroid, where you have no atmosphere. You can see a very strong thermal contrast between the daytime temperatures, which is from here to there, which reach up to 300 Kelvin, and then as the night settles, you have a very extreme drop in temperature down to 200 Kelvin about. So it's the thermal inertia is the property that governs the temperature response to illumination. And to illustrate that, you can go to a nice beach on a hot summer day, and you can experience thermal inertia as you walk over the beach, because massive rocks typically have a high thermal inertia of about 1,000. Sand has about a thermal inertia of about 250, and objects with a high thermal inertia heat up slowly, and when you walk over the beach, you will feel the heat, the sand, and when you walk over a rock, it will feel cold. And during the night, it's the other way around. The rocks are still hot, the sand cools down fast. This depends on the porosity and the grain size of the material. So when you have a massive rock, its porosity will govern its thermal inertia. The more porous it is, the lower is the thermal inertia. The finer the grains of the sand, the lower is the thermal inertia. And you can plug this thermal inertia in a thermal model that calculates the temperatures as a function of illumination, and you see this effect. So in blue is the curve with a low thermal inertia. You have very high temperatures during the day, very low temperatures during the night, and the temperature changes very quick. For high thermal inertia, it's the other way around. So the thermal model that I use solves the 1D heat conduction equation. So we neglect lateral heat conduction here. And maybe what's interesting here is the upper boundary condition. This is governed by the energy balance. So this term here is the energy lost via radiation. So this depends on the temperature to the power of 4, which makes this model nonlinear. And the heat that is radiated into space is balanced by the amount of energy that is put into the surface by the sun. So this is the illumination, which depends on the incident angle, and this is the one minus the albedo of the surface. So this is how much of the sunlight is absorbed. And then you have on the very right, you have the amount of energy that is conducted into the surface. So this depends on the temperature gradient at the surface and the thermal inertia. And this term in the middle couples the temperature in one spot of the thermal model to all of the others, because this is the amount of infrared radiation received from other parts of the surface, because as other parts of the surface of the asteroid are also emitting energy because they have a finite non-zero temperature, part of this energy will be received by the spot that you're modeling. So this gives you a coupled system, which you're then trying to solve. We are using so I coupled this thermal model to a digital terrain model of the landing site. So it's a multi-resolution model. So here's the landing site. The further you go out away, the further you go away from the landing site, the rougher gets the resolution of the terrain model. And as when you know the illumination, you can calculate the illumination from the geometry of this terrain model, and the illumination then determines then the temperature together with the material properties. So this is the boulder, a 3D model of the boulder that we observed, and this is the instrument field of view. So with this thermal model, I plug in the material parameters, and I get a time-dependent temperature for each point in the surface. And I can plug in then these results into a observation model, which then translates this to the instrument's observation. So this instrument observes a subset of the facets of this 3D model, and integrates them into a single signal. And this observation model is known from calibration. And also here, and part of these parameters go into this observation model. So here we have the thermal inertia and then the surface emissivity. The emissivity is the effectivity of the surface to lose energy via radiation. So emissivity is 1 when you have a perfect black body, and real objects have a emissivity smaller than 1. And this emissivity depends on the wavelength. And as we have different centers and different wavelength regimes, this is also a factor that goes into the observation model. And then this gives you the flux, the infrared flux, as a function of temperature and filter. And this is then the forecast of our system. We are, however, not so much interested in the state of the system as such. We are more interested into the parameters, and we're treating, and so we're augmenting and because we're trying to estimate the parameters of the system with the Ensemble Square filter technique, we are augmenting the state vector by including the material parameters into the state vector. And we also, and thus we need a forward model for the material parameters from Kalman filter iteration to the next one, and we do a random walk with this. So we plug in all the model parameters and include them in the forecast via a random walk forward model. Then we perform the Ensemble Square Root Filter, get an analysis, and plug in and repeat this whole iteration. And we have two constraints here. The thermal inertia must be larger than 0, and the emissivity cannot be smaller than 0 and not larger than 1. So these are physical constraints. Now, when we do this, we quickly converge to posterior distributions, which is shown in this slide here. So we have for each of the mole parameters, we get a posterior distribution which is almost Gaussian except for the emissivity, because the emissivity of the surface is so high that we are close to the physical boundary of a perfect black body. So here this distribution becomes very non-Gaussian. In terms of results, we find a very low thermal inertia of below 300. And this is very interesting. It has been also estimated in preliminary previous works, so this confirms those former studies. It is very interesting, though, because since we're observing a single boulder and not a field of sand, this means that this boulder is actually extremely porous, which is in line with the fact that we expect this asteroid to be very primitive. So this is a really cool result. And then overall, we have a very high emissivity. The overall emissivity, which is this is the emissivity that governs the overall radiative cooling, which is this is kind of an average emissivity. It's close to 0.98. And then when we look into the emissivity in the individual wavelength bands, we get very interesting results because we can get something like a spectrum from the surface. So we have the spectrum has several features which are characteristic for the material. One of this is the Christiansen feature. So this is the emissivity maximum. This is the part of the spectrum where the emissivity gets to 1. So it's each material has the Christiansen feature at a different frequency, and we can constrain this Christiansen feature to the 8 to 9.5 wavelength band. And then we have a general red spectral slope, which is indicative for space weathering. So the surface of Ryugu has been darkened and reddened during the course of time due to repeated heating and cooling of the surface and interaction with the solar wind. And then we have, interestingly, a very strong drop around 5 to 7 microns and from 9 to 11 microns. And that's very interesting because when you compare these to spectra of meteoroids, and I show you here 5 different spectra of meteoroids from so they are these meteoroids are carbonaceous chondrites, which are believed to be the most similar meteoroids on Earth, which are most similar to this asteroid. And you can see that in that region they vary quite a bit among each other. So we have, for example, this meteoroid here, which is called CV Allende. It is a thermally altered meteoroid, and you can see that, for example, here these two bands are switched. So the maximum is in the next band. This is much lower here, and this is clearly opposed to what we have. Whereas the CI Ivuna here shows pretty much exactly the spectrum that we see here. So with our results, we can say that the material on Ryugu is probably most similar to these kind of meteoroids. Also, what's interesting is that the strong difference between these two bands and this band indicates that there is very little dust on the surface of Ryugu, which is a surprise, but also confirmed by other instruments. But the question is, why is there no dust on the surface? And this is an open research question. Yeah. Um, so in summary, we use data simulation to simultaneously estimate all these thermophysical properties, which are the three parameters of our model. And the cool thing is here that since that we can use this data simulation tool, which is usually used to estimate the state of the system, also to retrieve its parameters, because due to the nature of the thermal model, its long computation time and the fact that we have quite a few free parameters makes it very difficult to use standard Monte Carlo methods. And the data simulation methods are actually very efficient in estimating these, and it works really well and it's very fast. In terms of results, it's really surprising and cool to see how porous this material on Ryugu is, because we're actually lacking meteoroids which have a similar porosity. So this can be a selection effect by the atmosphere, since very porous meteoroids will not survive the fall through the atmosphere. But it's also very cool because it means that this material from which this asteroid has formed is very similar to the very first material in the solar system. And the spectrum is also confirms this impression because it's similar to the most primitive meteors that we have on Earth. And if you have further questions, please feel free to contact me. And I'm at the end of my talk, so thanks a lot.
Thank you very much, Max. Are there maybe, let me have a quick look in the, I don't think there's any immediate questions in the Padlet, but so one question I have is the system, so the obviously the Ensemble Kalman filter versions are also dealing with nonlinearities, but is there any plan to somehow extend when it comes to the filter to approximation of a consistent filter, like some other version of filter to somehow deal better with nonlinearities and the parameters, or?
Well, I mean, you could think of this.
Mm-hmm.
Fortunately, while the system is nonlinear,
Mm-hmm.
it is not very toxic. It behaves really well, and the dependency on the parameters are not so drastic. So it's not chaotic in any sense. So all the parameters go into the temperature calculation in a nonlinear way, but small changes in the parameters do not result in large changes in the temperature. So it is, and you can see this in the posterior distributions, is in particular of the thermal inertia. It's almost Gaussian. So it's not so super nonlinear despite being nonlinear. So I think the Ensemble Kalman filter covers this really well, because if you actually calculate then the resulting observations which you get in your final Ensemble Kalman filter analysis step, and you compare these to the actual observations without using again a Kalman filter, just plugging these into the forward model and see what you get out of it, and it matches extremely well. So currently I have no plans to use a new particle filter or a hybrid filter for this.
There's actually now a question. Lars Neger is just typing. So the first part is, what distribution do you assume for the parameters? And are they consistent with the Gaussian assumption of the Kalman filter? I mean, I guess you partially already went into this a little bit now.
Yeah, so for the forward model, and if that's the question, the parameters themselves are distributed initially as Gaussians. So they do a random walk. So Well, actually, that's not true. At first, in the very first step, when I initialize the ensemble, I use a completely flat distribution. So everyone has the same probability, and then this quickly converges to a Gaussian distribution. But despite that the parameters are evolved through parameter space by this random walk, by adding a Gaussian noise factor to it, you still get the physical non-Gaussian properties into this distribution. So when I go back to the, for example, when you look closely, you will find that the thermal inertia is not really a Gaussian function. Actually, it is a little bit asymmetric, and this is also expected. So the temperature is more sensitive to thermal inertia changes in one direction than into the other direction.
I think Lars is maybe also he adjusted his question. So he said, do you get issues with negative parameters for those that should be positive? I guess you don't really have negative ones, but you do cut them off somehow.
I cut them off. Yes, in both steps, when the random walk or the analysis give me a non-physical value, I throw it out. So first I set it to I constrain it, and then in the final, when I finally look at the results, I throw out all non-physical ensemble members, and so the distribution that you see here is the remainder, so to say. And since since ensemble members have a realization of a parameter combination, if one of these parameters is non-physical, I throw the ensemble member out immediately. So that's
Okay, thank you so much.
Thank you.
Lars also says thanks for answering the question. So thank you.